Embedded systems are all around us. They typically run sophisticated software which interacts with the real world through hardware peripherals. But these hardware peripherals are prone to failure, and because they often fail asynchronously, it's a complex task for the programmer to anticipate and recover from these failures. So today I'll be presenting for you USENIX, a semi-automated peripheral recovery system based around lightweight checkpointing mechanisms. I'll be presenting four key contributions. First, the insights that drove the design of USENIX. Second, the three-step procedure that USENIX uses to recover from peripheral failures. Third, the mechanisms that implement this procedure. And finally, an evaluation on a series of micro-benchmarks and applications. USENIX was built upon OWL, an embedded Python runtime system developed at Rice, which allows the programmer to enjoy the productivity benefits associated with a managed runtime system for a high-level language, while also maintaining access to hardware peripherals through a native C function interface. So in USENIX, all peripheral accesses are structured as native C function calls. USENIX is motivated by two sets of insights. First, a broad set of insights into the unique characteristics of embedded systems and their ramifications on recovery. First, the external peripheral state needs to be recovered just like the internal program state. And so USENIX tracks and restores both kinds of state in the case of failure. Second, microcontrollers operate under extremely tight resource constraints. A typical mid-range microcontroller will have on the order of only 64 to 256 kilobytes of SRAM. And so, rather than taking a snapshot of the entire memory state of the system, USENIX logs only the memory that has actually been changed. In terms of time, microcontrollers have CPUs which operate at much lower speeds than those of conventional computing systems. And so to minimize the latency of recovery, USENIX enables rollback to the precise point of the failed peripheral access, minimizing the amount of work to be re-executed. The second set of insights that drove the design of USENIX are focused more specifically on the external state introduced by hardware peripherals. First, hardware peripherals can affect the external state in a variety of different ways, and based on this, they can be classified into four different categories. There are stateless peripherals, which have no effect on the external state, ephemeral, such as, for instance, an accelerometer, ephemeral peripherals, which have only a temporary effect on the external state, such as a buzzer, persistent peripherals, who have a more lasting effect on the external state, in the sense that their state is held as it was set by the last write to the peripheral until it's next written to. And an example here would be a motor, whose speed will remain as it was set. And finally, historical peripherals, whose state is similarly lasting, but is determined by a series of prior writes to it rather than by a single write. And an example would be an LCD display. Second, there are often dependencies between peripherals. And for the purposes of this talk, I'll define a dependency as follows. A peripheral P1 depends on a peripheral P2 if P2 failing results in P1 not having its intended effect on the external state. So consider the example of an autonomous car that is using a motor and steering servo to drive. Imagine that the car is trying to execute a turn. However, the motor fails. The steering servo is still going to succeed in causing the car's wheels to rotate, but it's not actually going to succeed in executing the intended turn. And so in this application, we'd say that the steering servo depended on the motor. Third, not all peripheral accesses can be replayed. In the case of accesses that depended on the failed peripheral, it's necessary to re-execute. But in the case of accesses that did not depend on the failed peripheral, in many cases it's actually incorrect to re-execute. And so in that case, we want to instead rematerialize, which we define as skipping during re-execution and instead just reinstating the old return value of the peripheral access function call. So at the beginning of redo mode, USENIX actually partitions all the peripherals into two different sets, a set of peripherals to redo and a set of peripherals to rematerialize based on these dependencies. Finally, the lasting state that persistent peripherals has requires a few additional steps. First, at the beginning of redo mode, all persistent peripherals need to be put into a safe state so that they're not operating erroneously during recovery. So for instance, with a motor, you'd probably want to set its speed to 0 so it doesn't continue running while you're doing the recovery process. Then, when we actually come to do re-execution, we need to make sure that its state is restored appropriately. And so if it's in the state of peripherals to redo, or rather the set of peripherals to redo, we want to restore for it the state that it held at the point of the failed access, because that way everything will be as it was during the original execution when we do the re-execution. But If it's in the set of peripherals to rematerialize, we want to instead leave it in its safe state for the duration of redo mode. And that way, at the end of redo mode, we can simply restore for it the final value that was rematerialized for it during re-execution, and it will be in the correct state going forward. So altogether, these insights motivated the three-step process that Phoenix uses to recover. It first rolls back the internal program state to the point of failure, so that all of the variables in the programmer's code are restored to the appropriate state. It then recovers the peripheral that failed, possibly by resetting it or swapping in a hot spare. And finally, it performs this redo mode execution process that I've described, in which it rematerializes or re-executes peripheral accesses on an individual peripheral access basis. That way, it ensures that all of the external peripheral state is in the appropriate state. So I'm going to return to the autonomous car example, actually a couple times throughout this talk. And here I'm going to introduce also an SD card, which it uses to log its motions. So we have, again, a dependency between the motor and steering servo, but the SD card does not depend on either of the two of them. So imagine that when we hit line 9, the write to the motor that was originally issued in line 3 fails. And we detect that. So the first thing that we do is we put both the motor and the steering servo, which are both persistent peripherals, into safe states, and we'll then roll back the state to line 3, where we actually issued the failed access. And this will effectively reset the value of the variable speed back to its original value of 100. Now we'll have to recover the motor, so it'll work correctly the second time, and we will redo the access to the motor. However, we're going to rematerialize line 4 because the SD card did not depend on the failed motor, and so it would actually be inaccurate to log the motor as having been set to 100 twice when in fact it failed the first time around. However, we'll redo line 5 because it only affects the internal state, which we've already rolled back. We'll also redo line 8 because there's a dependency between the servo and the motor, and we want to actually accomplish that turn that we were trying to do the first time around. Upon reaching line 9 once more, we'll exit redo mode and resume normal execution. So this procedure is implemented by a set of interlocking compiler and runtime system mechanisms. And at a high level, the runtime system has 4 key responsibilities. It automatically enables and disables checkpointing as appropriate. It logs the internal and external state whenever checkpointing is enabled. It detects the success and failure of all of the peripheral accesses, and in the case that a failure is detected, it executes the 3-step recovery procedure. The compiler, in turn, supports this runtime system process by injecting code to enable checkpointing and injecting code to track the outstanding peripheral accesses in the system, which in turn is used to disable checkpointing down the line. Phoenix divides the SRAM into 2 different heaps. A standard Python heap, which stores all of the internal program state, including the variables, and a separate, smaller recovery heap, which stores 3 different types of checkpointing structures. These structures are designed for efficiency, so they're only built up when checkpointing is enabled, and checkpointing is only enabled when there's actually a chance of failure, which in this case is when there are outstanding peripheral accesses. They're also built up incrementally and freed on a rolling basis as peripherals are acked. So, for instance, if all of the accesses before a given point in time have been acked, then we can free all of the checkpointing data that was populated prior to that point in time, even if there are outstanding peripheral accesses from later on in the execution, because it's no longer possible to roll back past that particular point. The first of these 3 checkpointing structures is the journal, which is used to log the internal program state. So during execution, whenever checkpointing is enabled, we log the internal program state by protecting the Python heap with the MPU. That way, every write to the Python heap generates a journal entry. And within this journal entry, we store both the address that was being written to, as well as its old contents. This allows us to roll back to the point of failure simply by doing a backwards pass over the journal, reinstating each address's old contents. Correspondingly, we have the rematerialization queues, which store all of the external peripheral states. We have 1 queue per peripheral, and 1 entry is generated per peripheral access. And these serve 2 different purposes. First, if this peripheral access fails, then we want to be able to roll back to a consistent state across all of the internal and external state. And so within this rematerialization queue entry, we store an index into the journal and pointers into all of the other rematerialization queues. Secondly, if a different peripheral access fails, it may be necessary to rematerialize this one. And so we store the arguments and return value of this peripheral access call in the case that that's needed. Finally, we have the control flow queue, which is used to drive redo mode execution. When checkpointing is enabled, it generates one entry per Python bytecode that's been executed. And then during redo mode, it determines when we actually exit redo mode and resume normal execution. So we'll potentially continue in redo mode until we re-reach the point at which the failure was detected, as in my early example. However, it's also possible to exit redo mode early. So for instance, if control flow diverges from the original path, such as by taking a different path at the original branch, then we'll exit redo mode early in order to adapt to this change in the state. So I'm going to go through a quick example of how all of these checkpointing structures are built up during normal execution. But actually, I'm going to leave out the control flow queue for simplicity because it really only becomes interesting when you get to redo mode. So at the beginning of time, we just have an empty journal, which is denoted by the first slot being -1. And checkpointing is not enabled yet because we haven't actually had any peripheral accesses. When the first peripheral access occurs, we get a new queue entry on the appropriate rematerialization queue, whose journal index is set to be the current value of next slot in the journal, which is currently 0. Now, because checkpointing is enabled as a result of that peripheral access, the write to the Python heap in line 3 will cause an entry to be filled within the journal. And because the first slot was previously -1 to the emptiness, the first slot will take the old value of next slot, and next slot will be incremented. In line 4, we get a different access to a different peripheral, which causes a new entry on a different rematerialization queue. And as you can see, its journal index is also set to be the current value of next slot, but now it's 1. Now, imagine that in line 5, the write to the motor in line 2 is act. In this case, we can free that queue entry and update first slot. So typically, first slot would actually be given now the earliest value of all of the journal indices across all of the live rematerialization queue entries, which right now is 1. But in this case, that would cause first slot and next slot to be equal. So that means the journal is empty again. And so we'll set the first slot back to -1. Okay, so the last runtime system mechanism that Phoenix uses is the set of recovery-oriented interrupt handlers, which we use to handle both the successful and unsuccessful peripheral accesses. In the case of a success, all we do is decrement the count of outstanding peripheral accesses, which is what we use to determine when we can disable checkpointing and/or free some subset of the checkpointing data as appropriate. But in the case of failure, we raise a flag indicating which peripheral failed, and we throw an exception to the Python interpreter requesting that it execute the 3-step rollback and recovery procedure. So all of these runtime system processes are supported at compile time in 2 different ways. First, the correct point to roll back to is not actually the failed peripheral access itself, but the first load of an argument for that peripheral access. And the reason for that is that these arguments might actually change during the recovery of the peripheral. For instance, if you swap in a hot spare, one of the arguments might change. And so you then would want to make sure that you're adapting to this and having the most updated arguments the second time through. And this is actually a pretty difficult point in time to detect at runtime in the interpreter, and so instead the compiler walks the abstract syntax tree and inserts a new journal store bytecode to enable checkpointing at all of these different points. Secondly, the compiler inserts code which tracks the outstanding peripheral accesses by incrementing a counter of outstanding accesses. And this is the same counter that's decremented on the previous slide, as I mentioned. Phoenix is designed to disentangle the peripheral recovery code from the application code as much as possible so that the application developer can write most of their code without having to worry about fault tolerance at all. But they do have to follow a couple of simple rules to make their application compatible with Phoenix. The most important one is that they need to define all of the peripherals within a class, which extends one of 4 Python superclasses that mirror the taxonomy I presented earlier. And within this, they need to define for us a recover function, which tells us how we should recover this particular peripheral if it fails. But they don't have to worry about any of the complex bookkeeping or control flow logic needed to determine when to fail this peripheral or how to restore all of the internal or other external state in the system, because Phoenix does all of that for them. They also may potentially need to define one or two additional restoration functions. So for instance, here we have an example of the motor, which is a persistent peripheral, and so it needs that safe state function that I mentioned earlier. But as you can see, both the recover and safe state functions are just a single line of Python code in this example, which is a realistic example that we used. So you can see the recovery code just switches over to a backup device, and the safe state code sets the motor speed to 0. The second thing that the programmer needs to do is they need to provide us with a config file which has a little bit of metadata about the peripherals in the system. And here the most important part is the dependencies between the peripherals. So you can see an excerpt of the config file that we used for the autonomous car, where there's an interdependency between the motor and the servo. For the evaluation, we used the Solaris LM3S9B892, which has a 96 kilobytes of SRAM, of which we carved off a 64 kilobyte heap for the standard Python heap. And we used a series of micro benchmarks, which used two peripherals, a gyroscope and compass, and performed a combination of reads, writes, and computation in a loop. We also evaluated Phoenix on 3 different realistic applications, which used a wider range of peripherals, varying from stateless to historical, and which also are representative of 3 different peripheral access patterns. In terms of space, Phoenix did really well. It only took about 4 to 5 kilobytes of SRAM to store all of the checkpointing data for these benchmarks, which allowed us to store multiple simultaneous overlapping checkpoints in a small fraction of the size of the overall heap. And as you can see, most of this space was actually taken up just due to the checkpointing structures themselves. There was only a small amount of additional metadata that was needed to be stored in the case that failure occurred. The largest of the 3 checkpointing structures was actually the journal, which we fixed at a size of 3 kilobytes for evaluation, but it never filled to more than 59% capacity across all of the micro benchmarks and applications. The applications fared similarly, with approximately 5 to 6 kilobytes of space required. The reason being that they were slightly larger was just that they had a few more peripherals in the system, and so they required a few more live rematerialization queue entries at any given time. In terms of time, it took from 12 to 143 milliseconds to recover from a failure. This involves all 3 of the steps, so the rollback, the recovery of the peripheral, and the re-execution process, which is what accounts for such big variance there, because the recover function could vary from application to application, and also the actual re-execution amount depends on how long it took to actually recognize that there was in fact a failure. The biggest time overhead, however, was actually due to the journal, because we implemented the journal in software for our prototype here. And as a result of that, there was an overhead of 6.2 microseconds for each store that was burdened by a little bit by this overhead due to journaling. However, in the paper, we actually proposed a few very simple hardware mechanisms that we believe would decrease this overhead by 2 orders of magnitude. So that would be good. There was actually no discernible slowdown on 2 out of 3 applications despite this. The only one that showed any slowdown was the virtual compass application, which basically was trying to read from a rangefinder and write to an LCD display as quickly as possible with basically no computation or rest in between iterations. And so because of this, checkpointing was enabled almost all the time, and we did notice a slowdown from this journaling store overhead. But the other 2 applications, which had much more realistic periodic peripheral access patterns, showed no overhead whatsoever from Phoenix. In conclusion, hardware peripherals introduce complex failure scenarios by bringing a combination of external state and asynchronous failure modes. But Phoenix greatly alleviates the burden on the programmer by using incremental checkpointing of both the internal and the external state, enabling precise rollback and correct recovery with minimal space overheads. That's it. Thanks.
Questions? I have a question. So you argued that Phoenix is designed for embedded system with very limited resources. What do you think if you re-implemented Phoenix in C instead of Python? How much gain would you get?
In terms of performance gains?
Resource, like memory, like performance, yes.
I don't know that Well, I do think the memory overhead would definitely probably decrease a bit because there is some journaling that is incurred just by the execution of the normal Python bytecodes there, and so there's a lot of internal stuff that's happening that's being logged that probably would be not necessary in C. So there would definitely be some improvements, but I'm not sure exactly what the quantification would be.
So I was wondering whether so your system is basically trying to put your the program into the original state, before failure. So I was wondering whether this is the correct kind of goal for embedded system. Because, for example, if your automatic driving car is at certain speed when the motor fails, and then at the next time it could be in front of a human being or something like that. If you still want to push it to the same speed, it could hit the person. Or when your motor, for example, burned out, and there must be a reason for that. And if you put your replacement and then put the same voltage on that, it will burn out again. So whether that's actually something you have been considering. Thanks.
Okay, well, I guess in the first case, I'm hoping that your application has a rangefinder that it's using. But in terms of in general, I think that sounds, honestly, to me like it's more something that should be handled at the application level, because these sound like major flaws in the application. And if the system wants to detect that there are, that the application developer has chosen an improper voltage to use their application and wants to adapt based on that, that sounds like a great plan and maybe something that's orthogonal to this.
Yeah, because you are actually trying to automatically basically roll back to the state, which usually this is unpredicted because, for example, there's something hidden in the your motor is jammed, for example. That's usually the case for the motor to burn out, for example. And then if your tool chain basically assumes that if I imagine I have already anticipated that, then that's why usually for most of the mission critical system, they always back to a safe place. For example, for robotics, they will go back to the non-motion state when there's a failure or when there's something unexpected happening. So you don't want to try to get back to the original state. If your tool chain automatically support that, something I haven't been expecting, and then it will try to do that again, it will fail again.
That's fair. So I think you could definitely say that there's a class of applications that might not be the most appropriate to use with this, but I think there's also a large class of applications with which it's appropriate.
Thanks, speaker again.